There is a question that settles into the mind like dust on ancient stone, quiet and persistent, asking us to consider something that makes us smaller than we thought we were. What if we are not the first? What if this earth, with its patient turning and its slow breath of seasons, has watched other minds come and go, other hands shape tools, other eyes look up at the same stars we think belong to us alone? The ground beneath your feet has been here for 4.5 billion years, and in that vast stretch of time, time so deep it drowns human comprehension, entire worlds have risen and fallen into silence. We know this much. The rocks tell us of oceans where deserts now stretch, of forests turn to coal, of creatures so strange they seem like dreams. But what if some of those dreams were thinking dreams? What if consciousness itself is not new to this planet, but merely recurring? Consider the weight of deep time pressing down on every moment. 1 million years is nothing. A brief flutter in Earth's long memory. 10 million years, still barely a whisper. But stretch your mind further to 100 million years ago, when the continents themselves wore different shapes and the climate breathed different rhythms. In such spans of time, entire evolutionary experiments could unfold, reach complexity beyond our imagining, and then dissolve back into the patient stone as if they had never been at all. The fossil record, for all its wonders, is a book with most of its pages missing. Preservation is the exception, not the rule. Soft tissues decay, behaviors leave no trace, and even bones crumble back to dust if the conditions are not precisely right. We see dinosaurs because their bones were large and their deaths happened in the right places at the right times. But what of smaller things? What of things that built with materials that do not fossilize? What of minds that may have been too brief, or too careful, or simply too unlucky to leave the kinds of traces we know how to read? There is something humbling in this uncertainty, something that makes us question our place in the great parade of being. We have grown comfortable thinking of ourselves as the crown of creation, the first and only species to look inward and wonder at our own existence. But the Earth is old beyond our ability to truly grasp, and in that oldness lies room for histories we have never imagined. Perhaps consciousness is not a recent invention, but an ancient one, emerging and fading like waves on a shore we cannot see. Perhaps intelligence has flowered before in forms so different from our own that we would not recognize it even if we found its traces. Perhaps the very air we breathe carries molecules that once passed through other thinking beings, other questioners, other dreamers who looked up at the night sky and wondered, as we do now, whether they were alone. The mathematics of possibility stretch wide across deep time. If life can emerge once, it can emerge again. If complexity can build once, it can build differently. If minds can kindle once, they can kindle in shapes we have never conceived. The universe seems patient enough and time generous enough to allow for experiments we cannot even name. And yet here we are, walking on ground that may have supported other footsteps, breathing air that may have filled other lungs, thinking thoughts that may echo other thoughts across millions of years of silence. We tell ourselves we are the inheritors of this world, but what if we are simply its current tenants, temporary custodians of a stage that has seen many performances? The question follows us into our sleep and wakes with us in the morning. Are we unique, or are we simply next? The Earth turns as it has always turned, patient and mysterious, keeping its secrets in stone and shadow, in the spaces between what we know and what we assume. Sometimes we find footprints in mud that harden to stone, the actual steps of creatures walking toward futures they could not imagine. Sometimes we find coprolites, fossil dung, that tell us what ancient creatures ate and how they lived, intimate details preserved in the least romantic of monuments. And in these surprises, these unexpected gifts from deep time, we glimpse the possibility that the stone may be holding other secrets, other whispers from minds and moments we have not yet learned to hear. The isotopes in ancient rocks speak of atmospheric compositions that changed over millions of years, but could some of those changes be signatures of biological activity we do not recognize? The trace fossils of burrows and tracks speak of behaviors, but could some of those behaviors be more complex than we imagine? The stone keeps its counsel, patient and mysterious, holding its secrets in structures too small for naked eyes and processes too slow for human lifespans to comprehend. But it remembers in its molecular way, and sometimes If we ask the right questions with the right tools, it consents to share what it has seen. In laboratories around the world, scientists tease isotopes from ancient rocks and read in their ratios the stories of vanished atmospheres and extinct metabolisms, chemical signatures of life forms that breathed different air and swam in different seas. Yet for all our cleverness in reading stone, we must remain humble before its silence. The rocks remember, yes, but they remember selectively, preserving some moments and losing others, according to laws we understand, but cannot control. And so we are left to wonder, what else might the stone be remembering that we have not yet learned to ask about? What other whispers from deep time he waiting in the patient archives of mineral and sediment, in the spaces between what we know and what the earth has seen? Time moves differently when you think in geological scales. Minutes become meaningless, years fade to insignificance, and even millennia compress into moments barely worth noticing. It means ice ages that scour landscapes clean and volcanic episodes that bury entire regions under layers of molten rock. It means the relentless chemical weathering that turns mountains into sand and sand into sediment, crushing and transforming everything in the patient mill of geological process. Consider our own civilization's likely legacy. What would remain of us after 100 million years of such processing? Our cities are built largely of concrete and steel, materials that will oxidize and crumble given enough time and weather. Our plastics might persist longer, but even they would eventually break down under enough ultraviolet radiation and chemical stress. Our roads would crack and be overgrown, our buildings would collapse and be buried, our satellites would fall from orbit and burn up in the atmosphere or crash into surfaces that would weather them away. The nuclear isotopes from our weapons and power plants would persist, yes, but as subtle chemical signatures scattered through rock layers, not as obvious monuments to technological achievement. Perhaps some of our electronics would leave traces, rare earth elements concentrated in patterns that might seem anomalous to future geologists, but even these would be ambiguous signs, potentially explicable by natural processes we had not considered. And if our own civilization, with all its concrete and steel and nuclear fire, would leave such subtle traces across deep time, what of others that might have built with different materials, different approaches, different relationships to their environment? What of intelligences that learned to work with stone and wood, that shaped their world through biotechnology rather than metallurgy, that left their mark in forms we would not think to look for? The fossil record shows us that life has experimented with complexity many times before. The Cambrian explosion brought forth body plans so strange that early paleontologists could barely believe they were real. The Carboniferous period saw forests of giant ferns and insects the size of birds. The Permian period ended with the Great Dying, an extinction so severe that it nearly ended complex life entirely. Each era brought its own experiments in form and function, its own solutions to the puzzle of how to be alive in a changing world. But complexity of form does not necessarily imply complexity of mind, and complexity of mind does not necessarily leave fossils. Intelligence might emerge and fade like weather systems, too brief and too ephemeral to register in the slow records of stone. A species might reach remarkable cognitive heights, might even develop technologies based on principles we have not discovered, and vanish during one of the many extinction events that punctuate Earth's history, leaving behind no more trace than a summer thunderstorm leaves in the sky. The extinction events themselves add another layer to this puzzle. Earth has experienced at least 5 major mass extinctions, episodes so severe that they reset the evolutionary clock and opened up new possibilities for life to explore. Between these major catastrophes, dozens of smaller extinction events have winnowed and shaped the flow of life, each one potentially erasing entire lineages and the accumulated knowledge they might have contained. From this perspective, we begin to see ourselves not as the inevitable culmination of evolution, but as the current inhabitants of a world that has seen many experiments come and go. We are riding a wave of complexity that has built up over millions of years of relatively stable climate and gentle evolutionary pressure. But there is no guarantee that this wave will continue, and no reason to think it is the first of its kind. The puzzle of deep time is not just about what happened in the past, it is about what remains unknowable across such vast scales of change and transformation. It is about recognizing that our perspective, shaped as it is by the brief span of human existence, may be fundamentally inadequate to grasp the full story of intelligence on Earth. We peer back through time like astronomers peering into space, seeing only the brightest signals from the deepest distances, missing entire galaxies of possibility in the darkness between. Dust is everywhere, so common that we barely notice it settling on our shelves, drifting in afternoon sunbeams, accumulating in the corners of rooms we thought we had cleaned. But dust is also one of nature's most eloquent storytellers, carrying within its microscopic grains the chemical signatures of distant places and ancient time. Each mote is a messenger, encoded with information about where it has been and what it has seen. If only we know how to read the language it speaks in isotopes and inclusions, in trace elements and crystalline structure. The dust that settles on your windowsill today began its journey somewhere else. Perhaps scraped from a mountain face by glacial ice, perhaps lifted from a desert by wind, perhaps exhaled from a volcano's throat as molten rock cooled and shattered into fragments, smaller than the eye can see. It has travelled on currents of air and water, mixing with other particles, picking up chemical hitchhikers, slowly accumulating the molecular evidence of its odyssey across the planet's surface. Scientists have learned to read this evidence with instruments so sensitive they can detect individual atoms, teasing apart the stories that dust tells about past climates and vanished ecosystems. Ice cores from Antarctica contain dust that fell as snow hundreds of thousands of years ago, each layer a snapshot of atmospheric conditions when our ancestors were still learning to control fire. The ratios of oxygen isotopes in this ancient dust speak of temperatures and precipitation patterns, while trace elements reveal which continents were donating sediment to the global atmospheric mix. But dust carries more than just climate data. It carries the chemical fingerprints of life itself, organic molecules that have survived the journey from their source to their final resting place, maintaining enough structural integrity to tell us something about the biological processes that created them. Pollen grains, microscopic and hardy, travel vast distances on the wind before settling into sediments where they can persist for millions of years. The waxy coating that protects these grains preserves not just their shape, but their chemical identity, allowing paleobotanists to reconstruct ancient ecosystems from samples no larger than a pinhead. And in this preservation, this patient accumulation of microscopic evidence, we glimpse the possibility that dust might be carrying other kinds of information as well. If pollen can survive for millions of years, what about other biological molecules? What about the chemical traces of metabolisms we do not recognize, signatures of life that operated according to principles we have not yet discovered? Consider the complexity hidden in a single grain of sediment from the deep ocean floor. Such a grain might contain fragments of shells from creatures that lived and died thousands of miles away, minerals precipitated from ancient seawater under conditions that no longer exist, and organic molecules from plankton that bloomed in response to climate patterns we can only guess at. The grain itself might have been transported by currents that carried it across entire ocean basins, tumbling and mixing with other particles as it settled slowly through kilometers of water toward its final resting place. But what if some of these particles carry information of a different kind entirely? What if, mixed in with the pollen and the shell fragments and the volcanic ash, there are traces of technologies we would not recognize as such? Materials engineered at the molecular level by intelligences that approached the manipulation of matter from directions we have not explored. Chemical signatures that speak not of natural processes but of artificial ones, so subtle or so ancient that they appear natural to our current methods of analysis. The possibility seems remote until we consider how much we are still learning about the chemical complexity of natural systems. Every year brings discoveries of new metabolic pathways, new ways that life manipulates matter at the molecular scale, new chemical signatures that we had previously attributed to non-biological processes. The boundary between the natural and the artificial becomes less clear when we realize that life itself is a kind of nanotechnology, building complex molecular machines with precision that our best laboratories are only beginning to match. And if life can create such molecular complexity through natural selection, what might directed intelligence accomplish given enough time and understanding? What kinds of materials might emerge from technologies based on principles we have not yet grasped? What kinds of chemical signatures might such technologies leave in the dust that settles over geological time? The archives of dust extend far beyond Earth's surface. Every sample of lunar soil contains particles that have been garnered by billions of years of meteorite impacts, mixing materials from across the solar system into a library of cosmic history. Mars carries dust storms that redistribute surface materials across the entire planet, creating a global record of Martian climate and geology that we are only beginning to learn to read. Even the dust between stars carries the chemical signatures of stellar evolution, the elemental inventory created by generations of stars that lived and died before our own solar system formed. In this vast circulation of matter, this cosmic recycling of atoms and molecules across space and time, we see both the persistence and the fragility of information. Some chemical signatures survive for billions of years, maintaining their identity across transformations that reshape worlds. Others fade quickly, their messages lost to heat or radiation or simple dilution in the vast mixing bowl of planetary process. The question that haunts us is not whether the dust remembers, clearly it does, in its own molecular way, but whether we are sophisticated enough to understand all the languages it speaks. We have learned to read some of its stories, the rise and fall of ice ages, the drift of continents, the evolution of Earth's atmosphere and oceans. But these are the obvious stories, written in chemical alphabets we have learned to recognize through decades of careful research. So what other stories might be written there? In scripts we have not yet learned to decipher? What other voices might be speaking from the dust that settles in layers across deep time, waiting for minds curious enough to listen and patient enough to learn their unfamiliar languages? In every grain that catches the afternoon light, in every mote that drifts past our attention, there might be messages from times and minds we have never imagined, encrypted in the universal language of atoms, but expressed in dialects we are only beginning to understand. There is a law woven into the fabric of reality that makes everything temporary. We call it entropy, this tendency of organized systems to gradually dissolve into randomness, of complex structures to slowly unravel into simpler forms. It operates everywhere, at every scale, from the decay of atomic nuclei to the heat death of stars, ensuring that nothing, no matter how carefully built or lovingly preserved, can maintain its form forever against the patient grinding of physical law. This law of dissolution affects more than just matter. It affects memory itself, the patterns of information that give structure and meaning to the world around us. Every record degrades over time. Every message becomes corrupted in transmission. Every trace of what was becomes fainter as the years accumulate, until even the most significant events fade into the background noise of a universe that tends inexorably toward forgetfulness. On Earth, entropy takes many forms. Water seeps into rock and expands when it freezes, cracking apart mountains grain by grain. Oxygen combines with iron in a slow burn that turns even the strongest metals to rust. Solar radiation breaks molecular bonds. Heat promotes chemical reactions that scramble organized structures, and time itself becomes an agent of dissolution, given enough patience to work its quiet transformations. But perhaps nowhere is entropy's action more profound than in its effect on the records of the past. Consider what it takes for information to survive across geological time. The pattern must be encoded in materials stable enough to resist chemical change. It must be protected from physical forces that would grind it to dust or scatter its components. It must avoid the recycling processes that constantly remake the Earth's surface, the subduction that drags ocean floors back into the mantle, the weathering that turns solid rock into sediment and sediment into new rock through cycles of burial and uplift. Even then, survival is not guaranteed. Information can become corrupted through partial preservation, its meaning lost when crucial contexts disappear. A fossil bone tells us something about anatomy, but nothing about behavior, social structure, or the thoughts that might have moved through the brain it once protected. A layer of unusual sediment might preserve the signature of a catastrophic event, but the cause of that catastrophe becomes a matter of inference and interpretation, subject to revision as new evidence emerges or old assumptions prove inadequate. This is the challenge facing any civilization that hopes to leave lasting records of its existence. The more complex the information, the more vulnerable it becomes to the action of entropy over time. Digital storage, for all its seeming permanence, depends on technologies that will become obsolete within decades. Magnetic media degrades. Optical discs become unreadable as the materials that encode information on them slowly break down. Even carved stone, seemingly eternal, succumbs to chemical weathering and physical erosion given enough centuries of wind and rain. And this raises a disturbing possibility. What if entropy itself has been an accomplice in erasing evidence of previous civilizations? What if the very laws of physics that make complex matter and complex information possible also ensure that such complexity cannot persist indefinitely? What if the universe, in its relentless drive toward equilibrium, has been systematically destroying the records of its own history, leaving us to piece together stories from fragments so incomplete that we cannot even recognize what we are missing? The mathematics of decay work against preservation in ways that become more extreme the further back we look. After 1 million years, most organic materials have completely decomposed. After 10 million years, even many minerals have altered beyond recognition. After 100 million years, entire mountain ranges have eroded away and whole ocean basins have opened and closed. The Earth itself becomes an agent of forgetting, recycling its materials through processes that scramble and transform everything they touch. Yet life has found ways to work with entropy rather than against it, to use the very processes of dissolution and renewal as sources of energy and opportunity. Evolution itself depends on imperfection, on the small errors and changes that accumulated variations make possible. Death makes room for birth, and decay provides nutrients for new growth. In the patient cycling of matter through living systems, information is not preserved, but continuously recreated, written and rewritten in the genetic codes that pass from generation to generation. But what if some forms of intelligence learn to work with these processes in ways we have not imagined? What if they develop technologies that used entropy as a tool rather than fighting against it as an enemy? What if they created systems that could maintain their essential information content even while allowing their material substrates to change and flow, like rivers that keep their identity even as the water that forms them is constantly replaced? Such technologies might leave traces so subtle that we would not recognize them as artificial. They might work through biological systems, using the genetic machinery of life to store and transmit information across spans of time that dwarf human history. They might operate through geological processes, encoding messages in the slow dance of plate tectonics or the patient accumulation of sediments. They might even use entropy itself as a medium, hiding information in patterns of decay and dissolution that would appear random to observers who did not know the key. The possibility is both fascinating and frustrating, because it suggests that evidence might be all around us, written in languages we do not know how to read. The background radiation that fills the universe carries the signature of cosmic inflation, events that happened when the universe was less than a second old. The rock layers beneath our feet preserve records of magnetic field reversals, ice ages, and mass extinctions spanning hundreds of millions of years. But these are the messages we have learned to decode because they speak in physical processes we understand. What other messages might be embedded in the data streams that flow around us constantly? What other forms of information might persist across deep time, encoded in media we have not learned to recognize as storage devices? In the quantum fluctuations of empty space, in the isotope ratios of ancient rocks, in the orbital mechanics of planets and moons, in the genetic sequences of organisms we think of as purely natural, how many layers of meaning might be hidden there? Waiting for minds sophisticated enough to recognize pattern buried within apparent randomness, entropy ensures that nothing lasts forever in its original form, but it does not necessarily ensure that information is lost completely. It may be transformed, scattered, encoded in new media, or preserved in ways that require entirely different approaches to decode and understand. And in that possibility lies both hope and uncertainty. hope that the records of the deep past might still exist in forms we have not yet learned to read, and uncertainty about whether we will ever develop the wisdom and patience necessary to hear what they are trying to tell us. In the early 1970s, a British science fiction television series posed a question that would eventually migrate from entertainment into the realm of serious scientific inquiry. What if humanity was not the first intelligent species to evolve on Earth? What if, millions of years ago, another civilization had risen to technological sophistication, built its own version of modernity, and then vanished so completely that we would have no easy way to detect their existence? The show called these hypothetical predecessors the Silurians, dating their civilization to a period when reptiles dominated the Earth's ecosystems. The fiction remained fiction for decades, but the question it raised began to seem less fantastic as scientists developed increasingly sophisticated methods for reading the deep history preserved in rocks and ice. If such a civilization had existed, would we be able to find evidence of it? And if we could not find such evidence, what would that tell us about our own chances of leaving a lasting mark on the geological record? In 2018, astrophysicist Gavin Schmidt and astrobiologist Adam Frank decided to take this question seriously. They called their investigation the Silurian hypothesis, acknowledging the debt to the television series while emphasizing that they were interested in the scientific principles involved rather than any specific scenario of reptilian intelligence. Their approach was both simple and profound. They asked what signatures an industrial civilization might leave in the geological record, and whether such signatures would be detectable after millions of years of geological processing. The results of their analysis were both reassuring and unsettling. Reassuring because they found that a truly industrial civilization would indeed leave traces that could persist across geological time. The large-scale burning of fossil fuels creates distinctive isotope signatures that alter the chemical composition of the atmosphere and oceans. The production of synthetic materials introduces entirely new chemical compounds into the environment. The mining and concentration of rare elements creates artificial distributions that would be difficult to explain through natural processes alone. But their analysis was also unsettling because it revealed how brief and subtle these signatures might be when viewed against the background of deep time. An industrial civilization that lasted for centuries or even millennia would register as barely more than a moment in the geological record, a thin spike in various chemical curves that would be easy to miss unless one knew exactly where and how to look for it. Even more troubling was their realization that our current methods of studying the deep past are poorly suited to detecting such brief events. We sample ice cores and rock layers at intervals that often span thousands of years, meaning that entire civilizations could rise and fall in the gaps between our data points. We focus our attention on the biggest and most obvious signals, mass extinctions, climate changes, major volcanic events, while the subtler traces of intelligence might hide in the noise we filter out as uninteresting. This methodological bias raises profound questions about our understanding of Earth's history. How many other brief episodes might we have missed? How many sudden changes in atmospheric chemistry have we attributed to natural causes when they might actually represent the signatures of intelligence operating on timescales too short for our geological perspective to resolve clearly, freely? The Silurian hypothesis does not argue that such civilizations actually existed. Instead, it asks us to confront the limitations of our knowledge and the assumptions that underlie our confidence about the uniqueness of human intelligence. It points out that the absence of evidence is not the same as evidence of absence, particularly when we are searching for phenomena that operate on vastly different timescales from those that dominate our experience. Consider what our own civilization would look like from this perspective. Human industrial activity has been intense for less than 3 centuries, barely a heartbeat in geological terms. Even if we continue our current trajectory for several more centuries, our entire technological episode would occupy a layer of rock so thin it would be difficult to distinguish from the effects of a large volcanic eruption or a major climate fluctuation. The chemical signatures we are creating The altered isotope ratios from fossil fuel burning, the synthetic compounds that do not occur in nature, the redistributed elements from mining and manufacturing would certainly be detectable if someone knew to look for them and had the tools to measure them accurately, but they would also be easy to miss or misinterpret, particularly if the observers came from a very different technological background and were not familiar with the specific processes that created these signatures. And this realization forces us to ask, if we would be difficult to detect after a few million years of geological processing, how confident can we be that others have not been equally difficult to detect? The methods we use to study the deep past were developed to answer questions about natural processes, the evolution of life, the drift of continents, the cycling of elements through the Earth system. They were not designed to search for intelligence, and they might not be sensitive to the kinds of traces that intelligence leaves behind. Moreover, our assumptions about what intelligence looks like are inevitably shaped by our own experience. Though we imagine advanced civilizations in terms of cities and factories, metals and plastics, energy consumption and waste production. But what if intelligence took different forms? What if some species learned to work with biological systems rather than against them, developing biotechnologies that would be indistinguishable from evolved organisms after a few million years? What if they found ways to meet their needs without the kind of large-scale environmental modification that characterizes our own approach to technology? The Silurian hypothesis does not provide answers to these questions, but it does something equally valuable. It makes the questions themselves scientifically respectable. It transforms speculation about pre-human intelligence from the realm of science fiction into a legitimate area of research with testable predictions and measurable consequences. In doing so, it also changes our relationship to our own civilizational project. If we take seriously the possibility that intelligence has emerged before, then our current moment becomes less unique, but perhaps more precious. We are not necessarily the first minds to contemplate the cosmos, but we might be the first with the tools and opportunity to search systematically for our predecessors. We might be the first with both the capability and the motivation to leave clear messages for those who come after us. The hypothesis reminds us that intelligence, even technological intelligence, might be less rare than we assume, but also more fragile. It suggests that the universe might be rich with the remains of civilizations that rose and fell before we learned to look for them. Civilizations whose greatest achievements have dissolved back into the patient anonymity of stone and sediment, leaving behind only the faintest whispers for those with ears sophisticated enough to listen. Imagine an archaeologist of the distant future, perhaps 50 million years from now, carefully excavating through layers of rock that once were our present moment. What would they find? What traces of our civilization would persist long enough to puzzle minds that might be as different from ours as we are from the trilobites whose remains we study today? Crichton is not merely academic. It forces us to confront both the hubris and the humility of our technological moment, to see ourselves as we might appear from the deep perspective of geological time. They would find first and perhaps most obviously our plastics. These synthetic polymers, designed for durability and resistance to decay, will outlast much of what we consider more substantial. The billions of tons of plastic we have created and discarded will become a distinctive layer in the sedimentary record, a horizon that future geologists might call the Anthropocene boundary, the moment when one species began reshaping the chemical composition of its planet's surface materials. But plastic is just the beginning of our technological signature. Future archaeologists will find layers enriched with elements that rarely occur in such concentrations naturally. The rare earth metals we mine for our electronics, the isotopes we create in our nuclear reactors. The synthetic chemicals we've invented for everything from pesticides to pharmaceuticals. These materials will persist as trace fossils of our technological metabolism, chemical signatures of processes that could not have occurred without directed intelligence. Our concrete and steel will leave their own marks, though perhaps not in the forms we might expect. The concrete will weather and crumble, but it will leave behind distinctive mineral assemblages, the products of cement chemistry mixed with whatever local materials we used as aggregate. Our steel will rust, but the iron oxides it creates will carry isotope signatures that reflect the industrial processes used to refine the metal from ore. Even our glass, seemingly fragile, will survive in fragments that preserve the chemical composition of the sands and additives we used to create it. Perhaps most intriguingly, future archaeologists will find what we might call technofossils, the preserved remains of our manufactured objects transformed by geological processes into something resembling natural fossils. Circuit boards might survive as thin films of metal and silicon, their intricate patterns preserved like the delicate tracery of ancient leaves. The hard drives that store our data might persist as magnetized mineral grains, their information content long since scrambled, but their artificial origins still detectable through unusually regular patterns in their magnetic domains. Our satellites and space debris will leave their own archaeological traces, not in Earth's rocks, but in the cratered surfaces of the Moon and other airless bodies in our solar system. There, protected from the weathering that erases so much terrestrial evidence, the remains of our space age will persist for billions of years, landing sites and crashed probes becoming monuments more durable than any pyramid or cathedral we have built on Earth. But the most profound technofossils we are creating might be the biological ones. Our agricultural practices are reshaping the evolution of countless species, creating new varieties of plants and animals that carry the genetic signatures of human influence. These domesticated organisms might persist long after our civilization falls, evolving and diversifying, but always carrying in their DNA the evidence that they were once shaped by intelligence for purposes now forgotten. Even more subtly, we are leaving traces in the evolutionary trajectories of wild species. Our antibiotics are selecting for resistant bacteria. Our pesticides are driving the evolution of insects. Our cities are creating new ecological niches that are being filled by rapidly evolving urban-adapted species. These evolutionary changes will persist and continue to ramify long after their original causes have disappeared, creating biological technofossils that encode the history of our interaction with the living world. The isotopic signatures we are creating might be the most durable technofossils of all. The carbon dioxide we have added to the atmosphere carries distinctive isotope ratios that reflect the fossil fuels we burned to produce it. These isotopes will be incorporated into shells and skeletons of marine organisms, creating a permanent record in limestone and other carbonate rocks. Future geologists will be able to read in these rocks not just the fact that atmospheric chemistry changed rapidly at our moment in time, but specific details about the sources of that change and the processes that created it. Our nuclear activities are creating entirely new isotopes, elements that would not exist naturally on Earth's surface in measurable quantities. Some of these are short-lived and will decay completely within centuries or millennia. But others will persist for millions of years, creating permanent markers in the geological record. Future scientists will find layers of sediment containing plutonium isotopes that could only have been created by nuclear fission, uranium isotopes that speak of enrichment processes, and trace elements activated by neutron bombardment in our reactors and weapons. Yet even as we consider these durable signatures, we must confront their fragility. 50 million years is a long time for a geologist studying recent events, but it is a brief moment compared to the age of complex life on Earth. Most of our technofossils will be concentrated in a thin layer representing just a few centuries of intense industrial activity. This layer will be buried under kilometers of sediment, heated and compressed by geological processes, mixed and scattered by the constant recycling of Earth's surface materials. Some signatures will survive this processing better than others. The isotopic traces will persist longest, incorporated into minerals that can withstand considerable heat and pressure. The biological signatures might evolve beyond recognition, but still carry detectable traces of their artificial origin. The physical artifacts will be transformed into unrecognizable forms, but might still be distinguished from purely natural materials through their chemical composition or structural organization. And this raises a troubling question. If our own technofossils will be so difficult to detect and interpret after tens of millions of years, How confident can we be that we would recognize the technofossils of previous civilizations? The methods we use to study ancient rocks and fossils were developed to understand natural processes. We look for the signatures we know how to interpret, the remains of biological evolution, the traces of climate change, the evidence of geological activity. But what if previous intelligences created their own technofossils, materials and isotopes and evolutionary changes that we encounter regularly in our studies of deep time, but interpret as natural phenomena? What if some of the puzzling features we find in ancient rocks, unusual chemical compositions, unexpected isotope ratios, evolutionary changes that seem too rapid or too coordinated to be easily explained by natural selection, actually represent the technological signatures of minds that worked with it and matter in ways we have not yet learned to recognize? The future archaeologists who study our remains will have the advantage of expecting to find intelligence. They will know to look for technological signatures and will develop methods specifically designed to detect and interpret them. But we, studying the deep past, approach the rocks with different assumptions and different tools. We look for the patterns we have learned to see, and we might be missing entirely the patterns left by minds that saw the world differently than we do. The Earth has ended worlds before. Not once or twice, but repeatedly, regularly, with a thoroughness that erases entire evolutionary experiments and opens up space for new forms of life to emerge and flourish. We call these events mass extinctions, but the term barely captures their profound impact on the history of life. They are more like planetary resets, moments when the accumulations of millions of years of evolutionary complexity are suddenly simplified, when the established patterns of existence are broken and the survivors must begin again in a world that has been fundamentally transformed. 5 times in the past half-billion years, extinction events have been severe enough to eliminate most of the species on Earth. The largest of these, the Great Dying at the end of the Permian period, removed perhaps 90% of all marine species and 70% of terrestrial vertebrates. The most famous, the asteroid impact at the end of the Cretaceous, eliminated the non-avian dinosaurs and cleared ecological space for mammals to diversify and eventually produce creatures capable of contemplating their own extinction. But these major events are only the most dramatic examples of a process that operates continuously at smaller scales. Earth's history is punctuated with regional extinctions, climate-driven population collapses, and ecosystem reorganizations that reshape the trajectory of evolution without necessarily registering as global catastrophes. Life on Earth exists in a state of constant flux, always adapting to changing conditions, always vulnerable to the next disruption that might exceed its capacity for adjustment. From our perspective, these extinctions appear as tragedies, the loss of irreplaceable forms and possibilities. But from the longer perspective of evolution itself, they might be better understood as opportunities, moments when the constraints of existing ecosystems are relaxed and new experiments become possible. Each extinction event is followed by what paleontologists call adaptive radiation, rapid diversification of the survivors into new ecological niches and new body plans, exploring possibilities that had been closed off by the presence of established competitors. The question that haunts us is whether intelligence itself might be subject to these same cycles of emergence and elimination. If consciousness and technology are simply other forms of biological complexity, then they too might be vulnerable to the same forces that have repeatedly reset the evolutionary experiments of the past. A species that had achieved technological sophistication might still find itself helpless against certain kinds of environmental catastrophe, particularly those that operate on timescales too rapid for social or technological adaptation to be effective. Consider the mechanisms by which mass extinctions operate. Some are sudden and violent, asteroid impacts that fill the atmosphere with debris, volcanic eruptions that poison the air and acidify the oceans. Others are gradual but inexorable, climate changes that outpace the ability of species to adapt or migrate, atmospheric changes that make certain metabolisms impossible to sustain. Still others operate through complex cascades, the collapse of key species that support entire food webs, the breakdown of biogeochemical cycles that maintain planetary habitability. An intelligent species might be able to protect itself against some of these threats. Technology could potentially deflect asteroids, build shelters against atmospheric toxins, or create closed-loop life support systems that could function even if natural ecosystems collapsed. But intelligence also creates new vulnerabilities. Complex civilizations depend on intricate networks of cooperation and resource flow that might be more fragile than the biological systems they replace. A species that had become dependent on technology might find itself less capable of surviving disruption than its pre-technological ancestors. Moreover, intelligence itself might become an extinction risk. A species capable of manipulating its environment on a planetary scale might also be capable of destabilizing the very systems that support its existence. Nuclear weapons, climate change, biotechnology, artificial intelligence, each represents a potential pathway through which a technological civilization might accidentally engineer its own extinction, becoming both victim and perpetrator of its own mass extinction event. And if such events have occurred before, what trace would they leave in the geological record? A civilization that destroyed itself through warfare might leave distinctive isotopic signatures from nuclear weapons, but these would be concentrated in a very thin time horizon and might be difficult to distinguish from natural radiation sources if discovered millions of years later. A civilization that triggered ecological collapse might leave chemical signatures similar to those created by natural climate changes or volcanic events. A civilization that simply exhausted its resource base and gradually declined might leave no clear signal at all, fading into the background noise of normal biological turnover. The fossil record shows us that life has remarkable resilience over geological timescales. No matter how severe the extinction, some forms of life survive and eventually diversify to refill the empty ecological niches. But this resilience operates at the level of life as a whole, not at the level of particular species or particular forms of complexity. The trilobites dominated marine ecosystems for hundreds of millions of years before finally succumbing to the Great Dying. The dinosaurs ruled terrestrial ecosystems for over 100 million years before falling victim to the asteroid that ended the Mesozoic era. Intelligence, as we currently understand it, has existed on Earth for a tiny fraction of the time that life itself has persisted. Our own species has been technologically sophisticated for less than 0.1% of the time that complex life has existed. We have no data on whether intelligence tends to be more or less durable than other forms of biological complexity when confronted with planetary scale disruptions. But we do know that complexity itself is vulnerable. The more specialized an organism becomes, the more dependent it is on specific environmental conditions remaining stable. The more intricate an ecosystem becomes, the more likely it is that the failure of key components will trigger cascading collapses. And perhaps the more sophisticated a civilization becomes, the more vulnerable it is to disruptions that exceed the parameters it was designed to handle. This perspective transforms our understanding of our current moment in Earth's history. We are not necessarily the culmination of an inevitable process, the final achievement of evolution's long experiment with intelligence. We might instead be participants in one iteration of a cycle that has occurred before and might occur again. Minds that have emerged during a period of relative planetary stability but remain vulnerable to the same forces that have reset Earth's evolutionary experiments repeatedly throughout the deep past. The possibility is both humbling and hopeful. Humbling because it suggests that our achievements, however remarkable they might seem to us, are not necessarily permanent or unique in the context of deep time. But hopeful because it implies that intelligence itself might be a reproducible phenomenon, something that emerges naturally from the evolutionary process given sufficient time and appropriate conditions. If we are not the first, we might not be the last. If consciousness has kindled before, it might kindle again, perhaps in forms we cannot imagine, rising from the ashes of extinctions we cannot prevent and learning lessons from failures we cannot foresee. The ocean floor is Earth's largest cemetery, a vast repository of sediments that have accumulated grain by grain over millions of years. preserving in their layers the history of everything that has lived and died in the waters above. But it is also Earth's most active recycling centre, where the planet's tectonic machinery constantly consumes its own past, dragging ancient seafloor back into the mantle and erasing evidence that might otherwise persist for billions of years. This dual nature, preservation and destruction operating simultaneously, makes the ocean floor both the most promising and the most frustrating place to search for evidence of deep history. In some places, sediment cores reveal records stretching back hundreds of millions of years, each layer a snapshot of ancient climate and ocean chemistry, each sample containing the microscopic remains of countless organisms that lived and died in waters that no longer exist. But in other places, entire oceans have opened and closed, their seafloors consumed by subduction zones and replaced by new crust rising from mid-ocean ridges, taking with them any evidence they might have contained of the worlds they once supported. The mathematics of this process are sobering. The oldest seafloor on Earth today is less than 200 million years old, ancient by human standards, but barely a 20th of the planet's total age. Everything older has been recycled, ground up and mixed back into the mantle through the relentless operation of plate tectonics. Entire ocean basins have disappeared completely, their existence known to us only through indirect evidence preserved in the continental rocks that once bordered their shores. But what might those vanished ocean basins have contained? What evidence might have settled onto their floors during the billions of years before their destruction? The deep ocean today receives a constant rain of material from the surface waters above, the shells and skeletons of planktonic organisms, particles of dust blown from distant continents, microscopic fragments of everything that lives and dies in the sunlit waters near the surface. This marine snow settles slowly through kilometers of water, accumulating on the seafloor in layers that record the passage of seasons, years and centuries with remarkable fidelity. If intelligence has existed in Earth's oceans, either native marine intelligence or traces of land-based civilizations carried to sea by rivers and winds, then evidence of that intelligence would likely have settled to the ocean floor along with everything else. The deep sea floor is remarkably good at preserving delicate structures that would quickly decay in more active environments. Organic molecules can persist in cold, oxygen-poor deep-sea sediments for millions of years. Microscopic shells maintain their intricate detail across geological timescales. Even fragile biological materials can be preserved if they are buried quickly enough to escape the attention of scavenging organisms. Even the same tectonic processes that destroy old seafloor also limit our ability to search it for evidence of ancient intelligence. Most of the ocean floor that exists today formed during the Mesozoic and Cenozoic eras, the time of the dinosaurs and mammals. If intelligence existed during earlier periods, when different ocean basins covered the Earth's surface, the physical evidence would have been recycled along with the rocks that contained it. This recycling is not random or uniform. Subduction zones, the deep-sea trenches where oceanic crust descends back into the mantle, are selective in what they preserve and what they destroy. Lighter materials tend to be scraped off the descending seafloor and accreted onto the continental margins, while heavier materials are carried down into the mantle and lost forever. This process creates a complex sorting mechanism that might concentrate certain kinds of evidence while eliminating others entirely. Moreover, the ocean basins themselves have changed dramatically over time. The Atlantic Ocean did not exist 200 million years ago. In its place was the supercontinent Pangaea, surrounded by the vast Panthalassic Ocean that covered most of the planet's surface. The Mediterranean Sea is the shrunken remnant of the ancient Tethys Ocean that once separated Europe from Africa. The Pacific Ocean, though it contains the world's oldest remaining seafloor, is itself much smaller than it was in the past, having been gradually consumed by subduction zones around its margins. Each of these vanished ocean basins would have had its own history of sedimentation, its own record of whatever lived and died in its waters. If marine intelligence evolved during the Paleozoic era, its remains might now be scattered through the mantle beneath the Atlantic Ocean, mixed into the convecting rock, that drives plate tectonics. The planet itself becomes a vast storage device, encoding information about its own past in layers of sediment and stone, in the isotopic composition of ancient atmospheres, trapped in ice, in the magnetic stripes that record the wandering of its poles across millions of years. These memories are written in languages we are still learning to read. The ratio of oxygen isotopes in fossil shells speaks of ancient ocean temperatures. The orientation of magnetic minerals in basalt flows records the direction of the Earth's magnetic field when the rock was young. The trace elements in ice cores reveal the atmospheric chemistry of vanished climates, while the pollen grains embedded in sediments tell stories of forests that grew when the continents wore different shapes and the seasons followed different rhythms. But planetary memory is vast and layered, containing far more information than we have yet learned to decode. Every grain of sand carries isotopic signatures that reveal its origin and history. Every crystal formation preserves evidence of the conditions under which it grew. Every fossil contains not just the shape of vanished life, but chemical traces of the metabolism that once animated it, molecular fossils that can persist long after the organic matter itself has been replaced by minerals. The most ancient memories are often the most difficult to read. Time itself becomes an enemy of preservation, not through deliberate erasure, but through the gradual accumulation of changes that obscure original patterns. Heat and pressure alter crystal structures. Chemical weathering replaces original minerals with new ones. Tectonic forces fold and fracture rock, mixing layers that were once distinct and scrambling the chronological order of events they recorded. Yet even these alterations leave their own traces, creating secondary records that can sometimes be more informative than the primary ones they obscure. The degree of metamorphism in ancient rocks tells us about the temperatures and pressures they experienced during burial and mountain building. The products of chemical weathering reveal information about past climates and atmospheric compositions. Even the fracture patterns in damaged crystals can preserve evidence of the forces that deformed them, stress fields frozen in stone like footprints in hardened mud. Some of the most remarkable planetary memories are preserved in ice, that crystallized form of water that can maintain its structure for hundreds of thousands of years under the right conditions. The ice sheets of Antarctica and Greenland are libraries of atmospheric history, their annual layers preserving samples of ancient air, along with the dust, pollen, and chemical traces that fell with each year's snowfall. In these frozen archives, we can read not just the story of changing climate, but also the signatures of volcanic eruptions, forest fires, and even meteorite impacts that occurred continents away from where the ice formed. But ice is a fragile medium for memory, vulnerable to melting and flow that can scramble its records or erase them entirely. The oldest ice on Earth is less than 1 million years old, a brief moment compared to the planet's total history. For deeper memories, we must turn to rock and mineral, substances that can preserve their records across billions of years if the conditions are right, and the processes of alteration work slowly enough to leave traces of original patterns. The magnetic memory of rocks offers some of the most precise records we have of ancient conditions. When igneous rocks cool, iron-bearing minerals align themselves with the Earth's magnetic field, creating a permanent record of that field's direction and strength at the moment of crystallization. These paleomagnetic records have revealed the wandering of continents across the Earth's surface, the periodic reversals of the magnetic field, and even changes in the rate of the planet's rotation recorded in the daily and seasonal rhythms of ancient coral growth. But what if some of these magnetic patterns reflect more than just natural processes? What if intelligence has learned to work with magnetic fields, creating technologies that leave their own signatures in the paleomagnetic record? The Earth's magnetic field is constantly changing, fluctuating on timescales from seconds to millions of years. Most of these changes appear random, the result of chaotic processes in the molten iron core that generates the field. But hidden within this apparent randomness, could there be patterns that speak of artificial manipulation, subtle modifications that would appear natural unless one knew what to look for? Similar questions arise when we consider the chemical memories preserved in rocks and sediments. The isotopic composition of carbon in ancient rocks tells us about the evolution of life and atmosphere, the cycling of organic matter through ecosystems, the burial of carbon in sediments, and its release through weathering and volcanism. But these natural processes create complex signatures that vary across space and time, making it difficult to distinguish between biological and technological sources of chemical change. What if some of the isotopic anomalies we find in ancient rocks reflect the activities of intelligence working with geochemical cycles in ways we do not recognize? What if civilizations have learned to manage planetary chemistry, subtly adjusting the composition of atmosphere and oceans to maintain conditions favorable for their continued existence? Such activities might leave traces in the isotopic record, but these traces might be so similar to natural variations that we would not think to look for them or would interpret them as evidence of biological rather than technological processes. The challenge of reading planetary memory is not just technical but conceptual. We approach the rocks with assumptions about what kinds of processes are possible and what kinds of signatures they should leave. We look for the patterns we know how to recognize, the evidence of evolution, climate change, and geological activity that fits within our current understanding of how planets and life interact. But planetary memory might contain information encoded in patterns we have not yet learned to see, messages written in languages we do not know exist. Moreover, the Earth's memory is not simply passive storage, but active process. The planet continuously rewrites its records, mixing old information with new, creating palimpsests where multiple histories are superimposed and partially obscured. The same processes that preserve some memories also destroy others, and the same rocks that contain clear evidence of some events might hold encrypted traces of many others, their signatures too subtle or too transformed to be easily recognized. Perhaps the most profound aspect of planetary memory is its potential longevity. While individual rocks and minerals can be altered or destroyed, the patterns they contain can sometimes be transferred to new media, copied and preserved in different forms across multiple cycles of destruction and recreation. Isotopic signatures can be inherited from older rocks during metamorphism. Magnetic patterns can be partially preserved even when the original minerals are replaced. Chemical traces can migrate through groundwater and be concentrated in new formations far from their original source. In this way, the Earth's memory becomes layered and distributed, with information scattered across multiple archives and encoded in multiple media. Reading such memory requires not just sophisticated instruments and careful analysis, but also the patience to piece together fragments of information from many sources to recognize patterns that span multiple scales of space and time, and to remain open to the possibility that the planet remembers more than we have yet learned to ask it about. There is something unsettling about the realization that you might not be unique. For most of human history, we have constructed our sense of identity around the assumption that consciousness is rare, that intelligence is precious, that minds like ours represent something unprecedented in the universe's long history. We are the species that names other species, the observers who contemplate observation itself, the questioners who wonder about the nature of questions. But what if this sense of uniqueness is itself an illusion, a kind of temporal narcissism that prevents us from seeing ourselves as part of a larger pattern? The possibility that intelligence has emerged before challenges more than just our scientific understanding of the past. It challenges our fundamental conception of what it means to be human, what it means to think, what it means to matter in a universe that seems so vast and indifferent to our concerns. If consciousness has flickered into existence multiple times across deep history, if minds have wondered about their place in the cosmos and then vanished back into silence, what does that say about the significance of our own wandering? But perhaps the question is backwards. Perhaps the recurring emergence of intelligence across geological time does not diminish our significance, but reveals something profound about the nature of existence itself. Perhaps consciousness is not an accident, but an inevitability, not a rare exception to the rules of physics, but a natural consequence of complexity reaching sufficient thresholds under the right conditions. Perhaps the universe tends toward awareness, given enough time and opportunity to experiment with different forms of organization and information processing. From this perspective, each emergence of intelligence becomes part of a larger story, a continuing exploration of what it means for matter to become aware of itself. We would not be the first chapter in this story, but we would not be merely repetitive either. Each instance of consciousness would bring its own perspective, its own questions, its own ways of experiencing and interpreting reality. The loss of previous intelligences would be genuine loss, representing unique viewpoints and possibilities that can never be perfectly reconstructed or replaced. Consider what this means for our understanding of extinction. We usually think of extinction as ending as the termination of evolutionary lineages and the closure of biological possibilities. But if intelligence emerges repeatedly from the evolutionary process, then extinction also becomes transformation, the clearing away of old forms to make space for new experiments in consciousness. Each mass extinction would be both catastrophe and opportunity, both ending and beginning, both loss and potential rebirth. This cyclical view of intelligence changes how we think about our own relationships with the future. If we are part of a recurring pattern, then our actions take on a different kind of significance. We become not just the creators of our own destiny, but also the inheritors of possibilities left by our predecessors and the architects of opportunities for our successors. The choices we make about technology, environment, and social organization become contributions to a longer conversation about what intelligence can be and do. But inheriting this perspective also means accepting a kind of cosmic loneliness that is both deeper and less complete than the loneliness of being unique. If intelligence has emerged before, then we are not alone in the deepest sense. Consciousness has kept cosmic company with itself across the eons, even if those instances never overlapped in time or communicated across the gaps between their existence. Yet we remain isolated within our own historical moment, unable to learn directly from those who came before or share directly with those who might come after. This isolation is not complete, though. If the Earth preserves memories of previous intelligences in forms we are learning to read, then communication across deep time becomes possible, though necessarily indirect and incomplete. The messages would be encoded in the chemical compositions of rocks, the isotopic signatures of ancient atmospheres, the biological traces of vanished ecosystems managed by minds we can barely imagine. Learning to read these messages would be like archaeology, but archaeology stretched across millions of years and requiring techniques we have not yet developed. The possibility also transforms our understanding of progress. Human civilization has constructed elaborate narratives about advancement and development, stories that assume intelligence naturally moves toward greater complexity, greater capability, greater understanding of the universe's fundamental nature. But if intelligence has emerged and vanished repeatedly, then these narratives become more complicated. Progress might be cyclical rather than linear, with each iteration of consciousness rediscovering principles and possibilities that previous iterations had also explored. Or perhaps each cycle explores different aspects of what intelligence can be, different solutions to the fundamental problems of existence, awareness, and meaning. One civilization might focus on understanding the physical universe, developing sciences that penetrate deep into the nature of matter and energy. Another might explore the possibilities of consciousness itself, developing technologies of mind that we cannot imagine. Still another might concentrate on harmony with biological systems, creating forms of intelligence that integrate seamlessly with the larger patterns of life on Earth. From this perspective, diversity of approach becomes more important than absolute advancement. Each iteration of intelligence would contribute unique insights to the larger exploration of possibility, even if those insights were not directly transmissible to later iterations. The universe would become richer through this multiplication of perspectives, even if individual civilizations remained mortal and ultimately transient. This view also suggests new ways of thinking about our responsibilities as conscious beings. If we are part of a recurring pattern, then our ethical obligations extend beyond our own species and our own historical moment. We become responsible for maintaining the conditions that make intelligence possible, for preserving the planetary systems that nurture the emergence of consciousness, for avoiding actions that might foreclose future possibilities for awareness to emerge and flourish. But we also become responsible for making our own contribution to the larger conversation, for exploring aspects of intelligence and existence that previous iterations might have missed, for pushing into territories of understanding and capability that expand the total range of what conscious beings can accomplish and experience. Our uniqueness would lie not in being the first or the only, but in being ourselves, in bringing our particular perspective and capabilities to the ongoing exploration of what it means for the universe to know itself. In this light, the question of whether we are alone becomes less important than the question of what we do with the consciousness we have been given. Whether we are the first minds to contemplate the cosmos or the latest in a long series, we remain responsible for the quality of our contemplation, the depth of our understanding, and the care with which we tend the conditions that make consciousness possible. We remain in each present moment, the universe's current attempt to understand itself, temporary but genuine expressions of the cosmos become aware of its own existence. Imagine them now, those future minds that will someday sift through the layers of our present moment, carefully excavating through rock that was once our air, analyzing isotopes that were once our breath. They might be human, evolved beyond recognition across millions of years of change and adaptation. They might be artificial, digital consciousnesses that have outlasted their biological creators and inherited the task of understanding deep history. They might be something else entirely, forms of intelligence we cannot imagine, emerging from evolutionary pathways we have not considered. But whatever they are, they will approach our remains with questions we can barely anticipate, using methods we cannot foresee to decode messages we never intended to send. They will read the signatures of our civilization in the chemistry of ancient rocks, trace the outlines of our existence in the fossil record we are unconsciously creating, piece together our story from fragments scattered across a planet that will have aged and changed in ways that make our current world seem like a dream. What will they make of us? Will they recognize in our techno-fossils the fingerprints of intelligence, or will our remains appear to them as the products of some unusual but natural process? Will they understand that the thin layer of plastic and concrete and altered isotopes represents the brief flowering of consciousness on a world that had been unconscious for billions of years, or will they classify our traces as just another biological anomaly? Like the oxygen crisis that transformed the early atmosphere, or the proliferation of shell-building organisms that marked the Cambrian explosion, the challenge they face will be immense. They will be trying to understand minds that thought in different categories, that organized reality according to principles they might not recognize, that solved problems using approaches they might not consider possible. Our technologies might seem primitive to them, or so alien that they mistake them for something else entirely. Our social structures might be incomprehensible to beings that organize themselves in ways we cannot imagine. Even our basic assumptions about identity, causation, and meaning might translate poorly across the vast gaps of time and evolutionary change. Yet, in another sense, they might understand us better than we understand ourselves. Distance in time, like distance in space, can provide perspective that proximity obscures. They will see our civilization as a complete story, with beginning, middle, and end visible from their temporal vantage point. They will be able to trace the consequences of our actions across millennia, to see patterns in our behavior that were invisible to us while we were living through them, to understand our place in the larger trajectory of intelligence on Earth in ways that we, caught in the middle of our own story, cannot. They will also have access to records we are creating unconsciously, signatures of our existence written in media we do not recognize as archives. The carbon isotope ratios in sedimentary rocks will tell them about our energy use and its atmospheric consequences. The distribution of synthetic elements will reveal the patterns of our industrial activity. The evolutionary changes we are triggering in other species will speak of our relationship to the biological world, our role as agents of environmental change, our impact on the larger systems that support life on Earth. on Earth. Either discovery would transform their understanding of their own existence, their own role in the ongoing experiment of awareness that began whenever the first minds flickered into existence and will continue until the last conscious moment fades into the cooling darkness of cosmic entropy. What they will not be able to recover is the subjective experience of being us, the immediate sensation of consciousness as we live it, the particular quality of wonder and confusion and hope that characterizes human awareness in our specific historical moment. They will reconstruct our technologies and trace our environmental impact, analyze our biology and model our social systems. But the inner texture of our experience will remain as inaccessible to them as the inner experience of trilobites remains to us. And perhaps this irreducible privacy of consciousness is what makes each iteration of intelligence precious despite its transience, what gives meaning to our questioning despite its ultimate futility. We will be remembered, but we will not be replicated. Our thoughts will leave traces, but other minds will have to think their own thoughts, ask their own questions, create their own meanings in dialogue with a universe that remains fundamentally mysterious, no matter how many times intelligence emerges to contemplate its nature. In the end, these future archaeologists of time will face the same fundamental questions that we face now, the same wonder about existence and meaning and identity that has driven consciousness since it first emerged from the unconscious operations of physics and chemistry and biological process. They will know more than we do about the history of intelligence, but they will still have to decide for themselves what to do with the knowledge they possess, how to live with consciousness in a universe that neither requires nor prevents awareness, how to create meaning in dialogue with the vast indifference of space and time. And in that sense, despite the millions of years and evolutionary changes that separate us, they will be our companions in the fundamental human adventure of being conscious in an unconscious universe. Fellow travelers in the ongoing exploration of what it means for matter to organize itself into patterns complex enough to contemplate their own existence, temporary expressions of the cosmos become aware of itself and wondering what to do with that awareness while it lasts. In the vast turning of deep time, consciousness appears and fades like waves on an endless shore, each iteration brief but genuine, each moment of awareness a small victory over the patient darkness that preceded it and will follow it again. We are the current wave, questioning and wondering, leaving traces for future archaeologists to decode, inheriting mysteries from predecessors we may never know existed, participating in a conversation that began before us and will continue after us. Adding our voice to the ongoing dialogue between mind and cosmos that gives meaning to existence, even as it reveals the ultimate impermanence of any particular form of consciousness. The Earth turns patient and mysterious, carrying forward the records of all who have wondered at their own existence, waiting for the next minds to emerge and begin again the eternal questions that make consciousness precious. Who are we? Where do we come from? Are we alone? And what shall we do with the brief gift of awareness while it burns bright against the encompassing dark?